This is problem 26.37, and we're told that a charge Q is placed on capacitor number 1. So this is capacitor number 1, and it has capacitance C. The capacitor number 1 is connected into the circuit as shown with an open switch, a resistor, and an initially uncharged capacitor. So this is capacitor number 2, and it has capacitance 3C, and initially it has Q is equal to 0. Now, what we do is we close the switch and we see how the current flows. So we see how the charge moves from here to this plate here. And we're asked to find the final potential difference between the plates of each capacitors. So we want to know what is delta V here, what is delta V here. Now let's go ahead and write the equations that we already know. So we know that delta V is equal to Q divided by C. And later on, we're going to need to know U, the energy stored on a plate, like a capacitor, is 1/2 C delta V squared. So what we need to realize is that these two capacitors are in parallel with one another when the switch is closed. Sure, here the wire has a resistor on it, that doesn't matter. As long as we don't go through another capacitor or a battery, we're in parallel. So what I mean by that is if there's another capacitor here, well then they're no longer in parallel with another. Or if there is a battery here, they're no longer in parallel. So because they're in parallel, we can reduce this down to one equivalent capacitor, like this, C equivalent. And we know that C equivalent for capacitors in parallel is just going to be the capacitance added up together, so C plus 3C. And that's equal to 4C. We also know that we can calculate delta V here as delta V equivalent is equal to Q divided by C equivalent. Now, the reason why we can do this is because we know that there's a total amount of charge Q in the system. Like Q is just going around. Sure, there's going to be some amount on this one and some amount on this one, but on the equivalent capacitor, it's going to hold all the charge Q. So we write this out like so, and C equivalent is just 4C, so we get this. Now, the reason why we did this specifically is because these guys are in parallel with one another, and we know that when things are in parallel, the delta V on the equivalent capacitor is the same delta V that's on this one and on this one. So delta V, capacitor 1, is equal to Q divided by 4C. Delta V2 is equal to Q divided by 4C. And that's our answer for A. Now B says, what is the charge on each of the capacitors? So for B, we know that Q1 is going to be equal to C1 delta V1, and that's going to be equal to C times Q divided by 4C, because the capacitance on number 1 is just C. And then Q2 is C2 delta V2 is equal to 3 times C. It has triple the capacitance, Q divided by 4C. And then if we just simplify this down, we get Q over 4, 3Q over 4. So what we see is that there's 1/4 of the original charge on the first capacitor and 3/4 of the original charge on the second. If we add them up together, we get total charge Q, which makes sense because that's what we had originally here. Now, C says, what is the final energy stored on each capacitor? We're going to have to use this equation up here. So this is the electric potential energy stored on a capacitor. We can write that out and we see that U is equal to 1/2 C delta V squared. Now U1 is equal to 1/2 C1 delta V1 squared. And we already know what all of these things are. So the capacitance was just C, and delta V was Q divided by 4C. And then for U2, same thing, 1/2 C2 delta V2 squared. And we know what delta V2 is, it's the same, but here we have 3C, Q divided by 4C squared. Now what we have here is 1/2 C Q squared divided by 16C squared, and then 1/2 3CQ squared divided by 16c squared, and that is going to give us q squared divided by 32c. And this is q squared times 3 divided by 32c. So this is the energy stored on capacitor number 1 and on capacitor number 2. The last question says, what is the internal energy appearing in the resistor? So the idea is, initially, we had a certain amount of energy here, and at the end, we had a certain amount of energy here, and a certain amount of energy here, plus some energy that left us in the resistor. So what we're going to have to do is figure out U resistor, so how much energy went to the resistor, and that's going to be equal to how much did we have initially minus how much did we have at the end, so UE1 plus UE2. And what was the initial potential energy? Well, originally, remember, we just had this one and it was charged and the circuit was open. So we need to figure out, well, what was the potential of just this one here? And we see that it has capacitance C and charge Q. So it's pretty simple. All we have to do is say that this was 1/2 C1 delta V1 initial squared. And that's going to be equal to 1/2 C Q divided by C squared, because it had all of the charge originally to itself. And that is 1/2 Q squared divided by C is the initial potential energy. So now U resistor is equal to that minus what we had at the end, which was, then we just add them up. We have Q squared divided by 32C plus 3Q squared divided by 32C. This is 4Q squared divided by 32C. Then we just have to subtract them. Here we can say, well, this is, multiply this by 16. So we get 16 out of 32 Q squared divided by C. That's just that minus 4Q squared divided by 32C, and that leaves us with 12. We simplify this one more time, and we get 3Q squared divided by 8C, and this is our final answer, and this is how much energy is appearing inside of the resistor, so how much energy the resistor is getting.